Our visual CAM for SOLIDWORKS is a gold certified product for SOLIDWORKS, and it works in SOLIDWORKS versions from 2011 all the way up to the latest 2018 version of SOLIDWORKS. So our latest version of Visual CAM is called Visual CAM 2018 for SOLIDWORKS, and it runs in SOLIDWORKS 2011 and newer versions. We have both for 64-bit and 32-bit. I know SOLIDWORKS has phased out 32-bit versions starting in 2015. If you are running an older version of SOLIDWORKS and also have 32-bit, you can run our CAM plugin as a 32-bit as well.
Okay.
So I have your assembly file that you had emailed us for the demonstration in here.
Right.
Right. So okay. So you can see that when you open up an assembly or when you open a part, you will see that there's a Visual CAM 2018 tab in there.
Yep.
So if you have the Visual CAM 2018 add-in installed and set to load, it will automatically show up if you're working in an assembly or if you're working inside a part. And this tab shows up in your command manager, and also as you go into the Visual CAM tab right next to your feature tree, you can go from the feature tree to the command manager by just a single click of a button.
Right.
So the CAM interface has two halves in the browser window. The top half is the machining browser, or we call it the machining operations browser. And then down at the bottom half, we have what is called the machining objects browser. And the machining operations browser has two main tabs here, which is program and the simulate. So your workflow is going from left to right as you work through each of these groups in here. And then in the simulate tab, you run a verification or a cut material simulation. Now down at the bottom, you have tabs where you can create tools, load tool libraries, you can define machining regions. We also do feature-based machining, and we have knowledge bases where we can create a workflow of operations and then apply those operations on other parts. So when you're working in an assembly here, the advantage or benefit of being able to work in assemblies is you can model your machining environment, or if you have multiple parts that you'd like to machine, you can basically lay them out in an assembly and you can program one or more parts. Now, you can also do the same thing in a part as well. If you have multi-body parts in a part, you can do them as well. So you can program in both part mode and in assembly mode, and I can show you both on this particular part. So looks like you have all your wires, everything modeled in here, and this is the part you're looking to machine. Is that right?
Yeah, and if you go to the SOLIDWORKS model for that, there should be a suppressed body in there that is the actual, that's the actual stock that I intended.
Yeah, so I noticed it here. So if I see it here, you have a stock that's defined right there. Okay, so it looks like it's about 4 1/4 inch by 6 inches, and then you have a 1/2 inch height, right?
Yep.
Okay, so there's a couple of ways to do it. One of them is I'm just going to leave it as hidden here. So if I go into the machining tab, and I'm going to define, first thing I'm going to define is the machining coordinate system. So if you take a look at the part, by default, the orientation of the coordinate system is in the same as what you have in SOLIDWORKS. So your z-axis is normal to this particular surface or face, and then you want to basically put the z normal to this particular face, right?
Yep.
Okay, and then you may also want to put the origin at a location which is maybe one of the corners of your stock blank or something like that. So the workflow here is, first step is you define your machine tool coordinate system. You can do it in several different ways. You can use these controls to spin the X, Y, Z coordinates, or you can say you want to set it to a surface. I can say I want to pick a surface, and I can pick this face and accept it, so the Z-axis will be perpendicular or normal to that face.
Great.
I can further go ahead and do rotations in here. So I want my X to be parallel to the edge, the longer edge, so I can go ahead and rotate it about the Z, and you can see the coordinate system is rotating. So now I rotate the X is parallel to the longer edge, the Y is parallel to the shorter edge, and now when I pick OK, you'll notice that the coordinate system for machining is established. So this is the world coordinate system that you have, but this is the coordinate system that we set up for machining. So you can toggle the display of both world and machining on and off. I'm just going to leave the machining coordinate system display on and off on here, okay?
Cool.
Any questions so far?
Nope.
Okay, so we've established the machine tool. The next step is to select the post processor in here. During our initial conversation, you had mentioned that you're going to be using a flash cut. So we have posts for a wide range of machine tools in there. There's over like 300 plus posts included. They're either listed by the name of the control or the machine tool in here. So we have a post for flash cut. We can output it with an automatic tool changer or just a flash cut post with a manual tool change. You can output in inches or millimeters. You can select that.
Yeah.
Flash cut can read .nc files. They can also read like .fgc or whatever the preferred extension is. You can select the extension from the list. If an extension is not found on the list, you can click on Add New to add a new extension to it.
Okay.
All right. The next step is we want to select, when you're working in assembly, you can select what parts that you like to machine. So if you do not pick any parts, it'll basically look at the entire, setup that you have in here, the entire environment you have as a part. So what we want to do is we only want to machine this part. I'm just going to double-click on parts, and I can just basically select this object in here, and it defines your part. You can see that the test part that you define is defined right in here. You can have one or more instances. You can select one or more parts. So that's what we defined here. Now I noticed that when I looked at this in the file, the stock what you have created is just about an inch offset from the part itself. So it's a half an inch on either side. So I can just go back and define my stock as a part box stock, and then I can specify an offset of half an inch in X, half an inch in Y, and Z is going to be the same height or the thickness of the part. So you can see it will uniformly extend in both directions by half an inch. So it's offsetting. Now that's one of the ways to define it. If you want to define a box stock by taking into account the extent of the part, I can select that also as a part, define it as a part, and then do a stock, box stock, and I hit copy model box. It'll compute the overall extent of the parts that you selected to establish the bounding extent of the stock for you.
So sorry, could you repeat that portion? So you said...
So if I select multiple parts in here and then do a copy model box, copy model bounding box, it looks at everything in here to compute the stock extents.
Okay. So
in this particular case, I only selected the part in here.
What if I had like a part that was had a extruded shape, for example, and I wanted to use that as my stock?
Okay. In our professional configuration, we have what is called a stock by selection. So I can actually go ahead and select this in here. I can select this solid object from the feature tree and then use what is called stock from selection, and it'll create a stock for you. So you can select it and then define it as a stock from selection. That's something we can do in our pro configuration. So it's not in standard configuration. You can do stock by extrusion also. You can pick a closed sketch and do an extrude stock, a planar sketch, or if you want to have your own stock model, you can define it and do a stock from selection.
Okay. Wonderful.
So there's different ways to do it. So in this particular case, it was just pretty straightforward here because it was slightly an inch overall, larger half an inch offset on each side. I just did a part box stock, and I put in those coordinates right there.
Yeah. Okay.
Okay. So you can see that the part is defined right in here. The next step is you want to establish your XYZ origins. You've already established your coordinate system orientation, but you want to define your XYZ origin. So by default, the origin is where the origin is located in your assembly or in the part. So you can insert what is called a work 0, and you can specify the location. So this could be like a G54 or G55. You work coordinate offset, and I can set it to one of these corners in here.
I think southwest is
center in a Z. Yep, southwest. So it's easy to do a touch off right there. And if you want to call that your G54, you can output a 54 right there.
Okay.
So now when you go ahead and take a look at your workpiece, you'll see that the 000 is set right up there to the top face in the southwest corner.
Perfect.
Any questions so far?
So how do you program the avoidance region?
Okay, so now we'll get into the programming part of it here. So now we would like to program, areas in here, right? So you want to basically be able to pocket these features in here, right? And then also cut this draft in here, right?
Yep.
On the part, and then do a profile to relieve the, cut it to the shape of the part.
Right.
So to program these in here, you basically go ahead and specify the operation. So I could, since this is all planar in here, these two pockets in here are planar. So what I could do is use a 2D.
That's interesting. That other one wasn't meant to be planar. That circle on the top was actually supposed to be a helical shape. But that's interesting. Anyway, just continue. That's fine.
Okay, so we could do it, if you want to do, if it's not planar, we can do a 3D toolpath. So we could just go in here and say, if it's planar, we could do like a pocket operation. So in this case, this is a slot. I can do a slot machining, and I can choose the features in here. I can just go ahead and right-click and say, select the loop or tangency in here. It selects the chain for us. And then I can go grab a tool. I can pick a tool that's exactly the same, the width as the slot that you have, or using a slot machining, or I can even go with a smaller tool. Specify the feeds and speeds. You can see that the feeds and speeds are being loaded from the tool, and you can always edit and add new tools in here as well. So I've defined tools of different types in here, and I can load them from my library. The feeds and speeds can also be established based on the material that you're cutting. Now, so once you define these tools, you can select them, so you don't have to go back and recreate the tools, or it's a nice thing. You can define everything and save it in your library. Now you can specify.
We plan on using manual tool change where we have end mills and collets. So
okay,
they're just standard R8 collets. So I notice a lot of these have the length specified and things like that. I guess how do you manage that when you're doing this manually? Do you have to measure it out to make sure that you have the same clearance, or is it okay if you just kind of eyeball it?
In Visual CAM, all the toolpaths are generated based on the tool tip. The tool length and information that you put in is going to help you in the simulation purposes. So as long as you're doing the touch off, you zero as the tip at the machine, you'll be fine.
Yeah, okay. That's what I thought. Okay, that's good to know.
Okay. And now I can specify my depths in here. I could say I want to pick the depth from the part. I can pick a top edge and then a bottom edge right there. And then that gives me the total depth. I can break it up into like multiple passes. Apply lead in and lead out, entry and exit, and then generate. So that will give me a pocket toolpath right there. So it's machining the slot. It's doing a slot machining operation. I can go to the Simulate tab and run a verification. So it's only cutting that particular feature that you selected. Now I can do a pocket operation or a profile in here. So since this is, inch and a quarter, and then so we can do a same tool. We can do a profile cut in here, and we can just go ahead and select one of these edges, and then I can specify a tool. I can specify my cutting conditions. I can choose which side to cut. I specify the cut levels in here. You can do apply entry and exit. You can ramp along the path, generate. So that'll get you a profile toolpath in here. You can always go back and make edits to any of the parameters and generate your toolpaths. Okay. Now you have this angled, there's a draft on the surface in here. So you can do like a 3D toolpath. If you only want to do like a finishing cut, you can go ahead and apply what is called a parallel finishing in here. And I can just go ahead and select these as my containment areas. So I'm picking those as my containment regions. I can switch it from a quarter inch go with a larger tool, then specify my cutting conditions in here. If you want to leave any stock or material above it, you can specify stock to leave. You can control the direction. The angle of cut controls which way you're cutting you. If you want to go along the length of the piece, then you want to run it parallel to the Y, so you put the angle as 90 degrees. If you want to run it parallel to the X, then you put in the angle as 0. You can control your step overs and then generate. So that basically gives you a 3-axis finishing operation.
Just out of curiosity, could you model in the 45 degree?
A 45 degree
toolpath. Yeah.
You want to put the tool at an angle?
Yeah, I'd just like to, see what the capability of it is, and I'm hoping that that'll show us, okay, maybe it'll run into the vise.
Yeah, so if you want to put it at an angle here, I can change the angle in here, go to cut parameters, angle of cut, I can put in 45. Now the tool is still normal to this particular face because the Z-axis, what you defined is normal to it, right? So now if you notice it here, that's your angle at 45.
So what do you recommend for cutting that shape? You recommend going along the length?
Well, you can either go along X or Y. It depends on the material you're cutting. If you're, sometimes when you're cutting wood, you want to avoid chipping. You may cutting, either along the length or the width might be better. As opposed to if you're cutting aluminum or if you're cutting metal, then you probably, would want to go along the length of it. You can also do climb or conventional cuts. If you only want to go in one direction, you have the option to set it to climb or conventional here. So instead of doing a mix, you can do climb only. So you basically cut one direction and then retract.
Okay.
So this is just a finishing pass. If you want to do roughing and then a finishing, we can certainly do that. So since there wasn't too much of material being left, that's where we do rough and finish, right? So in all these processes, what you notice here is we are only machining what areas we picked. It was not violating any of the areas, right? So you wouldn't run into any interference or collisions. Now, over here, you would want to relieve this material by cutting out a profile in here, right? So this is 1/2 inch, and you probably would not want to go all the way through, right? So you may want to leave like a tab or bridge, so at least the stock is being, the part and the stock are still intact, right?
Yeah.
So what we could do is we can add a profile cut. Now, before we do a profile cut, we can define a machining region. So in this regions tab, I can go ahead and select what is called a machining region. So the easiest way is I can do what is called a select surface edge areas, and I can right-click on this and do select tangency. It actually picks the entire loop, and I can accept that. So that basically creates a chain of edges, and now I can go into the regions tab and define what is called bridges. I can create bridge points in here. I can do automatic bridges, or I can even do manual bridges. I can pick which location I want the cutter to enter and leave. So I can first select my start point, and I'm going to move the start point right over here. You can notice that the start point changed, so I can define, so I would like the cutter to enter and leave from here, and then I can insert what is called automatic bridges, or I can do manual bridges, and I can specify the location of bridges in here. I would like to place one over here. I can place one over here. So you can basically choose where you want to place your bridge points. So you can also delete all the bridge points, and you can say you want to set up automatic bridge points. You can put like 4 of them. It'll place 4 bridge points, and now I can go ahead and edit these bridge points around, and I can specify where these bridge points needs to be placed.
So what does the bridge point actually look like once it's machined?
You can do a rectangular bridge, or you can do a triangular bridge. We'll go into the setup in just a moment.
Okay. So then the idea is that'll be, the stock will be hanging on by these bridge points, and then you machine those off later manually or something.
That is correct.
Okay.
Okay. So now we've defined the bridge points in here, and now we are ready to program toolpath for it. So you go into 2-axis. You can do a profile cut, and now you can select this predefined region that we created in here. You accept that as your selection. You go grab a tool. So I know if I use a 1/2 inch tool, I'm going to be running into this. I need to use a smaller tool, like a 1/4 inch, or something like a 3/8. I could pick a tool that's smaller than that, and then I can set my feeds and speeds. And in the cutting parameters, you can pick climb cut. You could choose the site to cut is outside. The cut levels, you can specify where you want to begin the cuts from. You want to start from this top face, and then you want to go down from this face down to this edge, which is going to be a 1/2 inch. So you can specify the total depth in here, or you can say the geometry is at the bottom. You specify a total depth in here, and you can specify in how many passes you want to cut. You could say you only want to go in like an 1/8 inch pass, so it'll give you 4 levels. You can control the entry and exit parameters, and then this is where you set your bridges, the type of bridge you would like to create, triangular, or you want to do rectangular, and you can specify the bridge height and the length. I could say I want to put in 300 thousandths as the bridge length. And the number of bridges is defined based on those points we created. Now when you generate it, you'll notice that it creates those bridges at those locations, precise locations where we defined it. So if I run a verification in here, you can actually see those bridges after you run a simulation. You can see those, it leaves those bridges. So you asked me what type of bridges are we creating. So this one, we chose a rectangular one. I gave it a thickness of 100 thousandths. I can change that from rectangular to a triangular bridge. I can go back into advanced cut. I can change it from rectangular to triangular and generate it again. So if I go back and run a verification, you'll see that it does like a triangular bridge where it kind of ramps down and ramps up. And you can control the bridge length and the height. And or in some cases, users like to leave a little bit of material at the bottom, so not cut all the way through. So you can leave like an onion skin if you don't want to leave bridges and tabs. So then you can basically easily break it up. So in this particular case, we did not have to specify, or in any of these, we can validate it by looking at it here. Now, in the case where you wanted to basically create like avoid areas and stuff like that, I'm going to show you how we can do that here. So I'm going to go over here and just basically go normal to that face, and then I will create a simple, very simple sketch in here, right? I'm going to create a new sketch, okay? and I will basically define a sketch. I can use convert entities, or I can say I want to define just a rectangular region in here. I could say this is the area I would like to define over here, right?
Yeah.
And then I'm going to define the same over here as well.
Yeah, as if we're using a toe clamp or something to clamp it into the into the bed.
Absolutely, absolutely. I'm going to define that. And so basically, you define the sketch. I'm also going to go ahead and say, create my geometry here. So I can use convert entities. And I can basically pick this as my geometry right there for cutting it, right? So I have basically two simple sketches in here. Now let's say I want to do a pocket machining, but I want to avoid these areas in here. So what I'm going to do here is go into two-axis pocket machining, and I'm going to select my sketch for machining is the one I created. This is the one I would like to cut, right? The boundary, what I selected, and then I can go to avoid regions, and I can select, again, I can select the curves or sketches. I can pick the sketch I define here. So I need to make sure my avoid regions is intersecting with the actual part region to avoid for clamp. So the system will automatically treat this out as the section not to be cut to. So if I go ahead and pick the same quarter-inch end mill, and I'll just give it a small depth in here of, let's say, we want to go like, 25 thousandths, and I'll generate the toolpath. So you will notice that now it actually avoids that area from being machined, if you notice in the toolpath, right?
Yeah.
So if I go ahead and run a verification, so I'll move it to the top of the tree, and I'm going to run a verification here. So we're doing like a pocket, and it's going to avoid this, so it automatically figured out the intersection of these two geometries in here. So you can do this both in part and also in assembly mode. So avoid basically will not cut into those. So if you just drop a sketch, I just use a rectangular sketch as an example, just to, so that, give you an illustration of how this works. It automatically figures out that those are the areas that you can cut into.
Yeah, perfect. Perfect, okay, yeah.
Right, and then once you have all of these programmed, I can go ahead and you can see that now I have the slot in there, which was the first operation. So you didn't really even have to model something in here. We just basically, programmed. And then once you have,
it looks like that's pretty graduated. That doesn't look like the draft there has the.
Yeah, because I used a flat mill here, I should have technically used like a ball mill to finish it because you have a draft on it, right? To get a better finish, you probably want to use a ball mill tool. So or even a corner radius tool might work better. So you can go into the tool, you can switch this from a flat mill to a corner radius tool, and it can go with a really fine step over, like a 10%. So that'll give you a very nice finish on it. So you can see this is a corner radius tool. If I switch it to a ball mill, you're going to get even a much finer finish.
Okay, yeah, cool.
And also the direction in which you're cutting, you can determine that.
Yeah.
Okay?
Beautiful.
So once you have these operations programmed, you could, since you're going to be using a manual tool change, you can do a post all. It'll post all the operations to one NC file. We can actually take a look at the post in here to see if the post is set up to output a tool number. So in this particular case, this flash cut inch post does not output a tool number because it's for a manual tool change. So what you could do is you can actually select the operations that you'd like to post it into one file. You can select like these first three operations. I can do a post, and I can specify, quarter-inch tool, or I can say rough cut.
Okay, I see. So you just have to upload the G as you do the tool change yourself manually.
Right. Yeah, there's some nice tools, features I can show you here is we can group these operations into a machining operation set, like a container or folder. I can select this and say this is for, quarter-inch tool, right?
Yeah.
I can just say 0.25 end mill, and I can take these three operations in here and then just drop it in here. And now this one is a different tool, and this one is you're using the same tool as this one here. So you can select the entire set and post it, so rather than having to do multi-select. So you can basically now notice that all the comments that you put in, the name of the operation are also showing up right in here. And if you also name the tool, you can output that as a comment. So I can go into the machining operation, right-click, and edit the tool, and I can basically put in a comment. I can say quarter-inch end mill.
Beautiful.
So when I do a change, I can do save edits to tool. And now you notice that these operations are flagged as dirty. All the operations that utilize the tool, right-click and regenerate, it's going to update all of them. Now when I post it, you'll notice that the comment that you put in on the tool shows up in the start of the code.
Okay.
So if you have an automatic tool changer, then we do have a post that can be output with the automatic tool changer. You just change it from FlashCut inch to ATC's automatic tool change.
Yeah.
Now this will output your tool numbers right there.
Yeah, we don't have that now, so or ever. I don't think. So do you also have backlash correction? Because we're using this Grizzly benchtop mill, and that thing has Acme screws instead of ball screws, and I understand that backlash correction is kind of an important factor.
I believe that's something you would set it up in the FlashCut control program, how to account for backlash. I know in Mach 3 there's a setting, so I'm sure there's a setting in FlashCut, so you can certainly talk to
I think there is.
FlashCut and they can.
Okay. So that's not in the actual
Now,
G code.
That is correct. Now we can output to very high precision. We could do 5 decimal accuracy or even 6 decimal. We can do double precision, but I believe 4 decimal is what's common for inch programming, and 3 decimal is for millimeter programming.
Beautiful. Okay.
So you can, saving your work in here automatically saves all of this information that you did into the same SOLIDWORKS assembly or a part document. Now, one of the nice features I wanted to point out here is knowledge base. So we can take all of these operations that we programmed and save them into a knowledge base. So when we have parts that are similar to these, we can actually load the knowledge base and then just, select the features to map it to associate to it for machining it. So, with the knowledge base, it makes your workflow a lot easier to work with it.
Great.
Now, also, I wanted to show you, we have some very nice features in our standard configuration. We have feature-based machining, which is called feature detection and machining. We can also do machining, of 3D parts. I'm going to go through a couple of examples with you. Before I do that, I want to ask, do you have any other questions on this particular, part that we demoed for you?
No, actually, I think I must have sent you the wrong file because I had a few more features on that, actually. But no, yeah, I'd love to see some of the 3D feature recognition that you guys have. That was my next question, actually.
All right. Give me just a moment, and we'll be able to go through that with you.
Yeah.
So what I have here is basically a prismatic part. Prismatic meaning you have, there aren't any drafts or sculpted bottoms, basically straight extrusions. So parts like these that if you have, it's very easy to program them. So we can go into this features tab in the machining objects browser, and you can do what is called automatic feature detection. So when you select this, it automatically identifies different features on a part. Like, for example, you might have hole features, you might have slot features, open pockets. You can see that all the features are detected in here. And as you select them, it also gives you information about the height for the silhouette feature. The planar face, it gives you a prismatic pocket. It tells you how deep the pocket is. It gives you information about open pockets and also the holes in here. You can also interactively select these features, and you can select them. If you right-click, it'll let you pick the type of operations that would be most appropriate for those features. So when I right-click on this prismatic pocket, it lets me either pick a pocketing and then do a finishing with the profile operation. Now we can also go one step further in here. Once we have these features detected, you can select the orientation and then just click on automatic feature machining. It'll actually apply the tool paths for each of the features that would be the most appropriate for it. You can see now it programmed a facing operation for an open pocket. It did a pocketing operation in here for the closed pocket, and then it followed up with a profiling operation for the exterior contour. You can basically go in and see it automatically does the programming for the slots as well. And you can basically define what is called a knowledge base to do the holes as well. So you can actually go into the features. You can select the feature right in here. And then if you right-click and say you want to apply a drilling operation in here, select the drilling. The features are automatically selected. You can automatically select the tool for it and then pick generate. So that creates your drilling operation. So this is
Beautiful.
feature-based machining, and we made a lot of improvements and added new features into our version 2018. Now the same part you can still do programming manually, where you can select the chain of edges and you can program it as well. So feature-based machining is very easy to use, and it's great for prismatic parts when you have parts that have no sculpted bottoms or there are planar faces, pockets, open pockets, holes. You can program them. You can do a combination of both, and you can always go back and edit these and say you want to change your cutting pattern on this one here. So instead of doing a offset, you can use the high-speed cut pattern, which is more like a tricaudal cut pattern, where basically you have a constant cutter engagement as you're cutting it. So if you run a verification in here, I'm also going to go ahead and apply what is called a color for the feature. So as you simulate it, you can see that each operation can be applied with a different color. So now you notice that this is basically a high-speed cut pattern where the toolpath maintains a constant cutter engagement. So it creates constant tangential arcs, so which basically prolongs your tool life.
Yeah, we'll see how rigid our system is and if it can handle this type of cutting, but it'd be really interesting. I think we'll have to do a lot of experimentation just to see what we're capable of.
So this comes included with the standard configuration, and you can use the offset, you can use the linear, so there's all other types of cut patterns. In addition to that, you also get the high-speed cut pattern as well.
Beautiful.
So in 2.5 axis, you'll have right from roughing all the way to T-slot machining in the standard configuration, and you get the whole machining where you have drilling, tap bore, and reverse bore. In 3 axis, you get 5 different types of methods: horizontal roughing, get parallel finishing, horizontal finishing, radial, and spiral as part of the standard configuration. Now in the Pro, you have all of the advanced 3-axis methods in here, which is part of the Pro. Now, do you typically have parts that require machining from multiple different orientations, like milling features from the top, from the bottom, or from the sides?
Yeah, we'll usually have a part that might require a couple different setups to, have some features on the side.
Okay, so in the standard, you can, in a given part, you can program from one setup or one orientation. So that means that if you need, this part needs to be machined from the top as well as from the bottom, then you would have to save as 2 files, one for the top and one for the bottom, and then you have to establish the coordinate system. So you basically establish the orientation of your X, Y, and Z. Now, in our higher configuration, that is the Pro, you have the ability to add additional setups in here. So you can program the top, and then you can create a new setup to program from the sides or bottom. So that's available in our higher configurations, but it is not in the standard. But if you would like to program in the standard, then you basically maintain 2 copies of the file, one for calling it the top side, one for the side, bottom side, or however you want to label it.
Yeah. Can you define the machine envelope?
The machine envelope, we really don't have to do it because it all depends on the part envelope and where you set the 0. So we don't have to define a work envelope for the machine.
Right, but if I wanted to machine in, or if I wanted to simulate like the machine itself.
Okay. We actually have what is called a machine tool simulation in here. So I'm going to go ahead and just put the 0 right here to the center right there. And then let me go ahead and generate this toolpath. So we do have a machine tool simulation that's available starting with our expert configuration and above. So we can go into load from file in here. And we can select the machine tool from the list. So I can go ahead and say I want to use a CNC mill as an example here. So you notice that displays the machine tool. Then as I go into the simulate tab, I can enable this, and then I can go ahead and run a verification with the machine tool. So the machine tool simulation comes included starting with the expert configuration of our product.
Yeah, okay.
So it basically shows simulation.
I feel a little more sophisticated than we need.
So this basically shows the simulation with the machine tool. You can see the linear X and the Y axis moving, and also the Z axis is basically, in this particular case, it's doing a 2.5 axis operation. So Z is remaining constant, and then it's basically retracting and transferring over to the next location.
Yeah.
So that would be, the machine tool simulation is not in the standard, but it comes right from expert level.
Right.
Okay, so let's look at a 3-axis example in here. Would you have any questions before I move into 3D?
Nope.
Okay. imported into SolidWorks, or you could be working with files that you natively built in SolidWorks. So this is basically a cavity. I can also have an example of a core. You can program all of these parts right from our standard configuration. So once you have a part imported or modeled in SolidWorks, the workflow is very similar. You define your machining coordinate system, and then you define the number of axes. So the standard automatically sets itself to 3 axes. You won't be able to pick 4 or 5 axes on the machine tool. And then you select your post. You define your stock material. So you can define your stock as a box stock or a part box stock. And then here you establish your work 0, the location of your X, Y, Z origin. And now in the 3 axis, we have different types of methods. So with the standard, you get starting with horizontal roughing. So this is a roughing in levels. Now you don't have to pick any areas. If you wanted to automatically rough based on the part and the stock that you define, you really don't have to pick any surfaces or boundaries in here. So the system will automatically analyze it and compute the toolpath. So you can specify your cutting conditions, your cut parameters, step overs, and all you do is generate. So even if you have Y's in here that is holding the stock plank, you can notice that since the extents of the stock, and this is the only cavity in the part, it knows to restrict the toolpath to the cavity only.
Very cool.
And I can run a verification in here. That's your roughing in levels. So there's your Z-level roughing operation. Now, after you're done with the roughing process, you could go to a pre-finishing operation, which could be like a parallel finishing, similar to what we did on one of your files. And I can pick a boundary in here. So I can right-click and say select tangents here, select loops. So it uses this as a containment to restrict the toolpath. And then I can pick a tool for it. I could say I want to go with a ball mill, specify the cutting conditions. You can specify like an angle or direction of cut. You step over in here. You can control how fine you want the cutter to step. And then you pick generate. So this gives you a finishing on the part you can see right there. If you want to swap the tool, let's say you want to go with a 1/4 inch instead of a 1/2 inch, you just drag and drop the tool on top of the operation, right-click and regenerate. The toolpaths are automatically computed.
Oh, wow. Very cool.
If you make a design change, you don't have to start over again. So you just have to go back, either reselect the boundaries if you added or you deleted some features or edges. So you just have to go back and reselect them. So you can also rotate view while you're simulating.
That's useful. Yeah.
So this is fully integrated into SolidWorks as you see it here. So that's the advantage of having an integrated system, is you don't have to export files, import files, and also you're staying within the same environment to be able to go from your design to toolpath. And if you make some changes, it's easy for you to update your toolpaths as well.
Fantastic.
So the simulation also comes included right from the standard configuration. So you have the advanced simulation module here. Now this is parallel finishing. So if you want to do finishing in levels, I'm going to just do a pause and then pick simulate to end. You'll notice that it runs the simulation all the way through the end. And once it's completed, it'll show you the final result of the cut material right there. So now, since you do a parallel, when you do a parallel finishing, you would end up with some scalloping, on the vertical walls, depending on the angle of the cut or direction of cut that you put in here. So you could go back and add another parallel finishing operation to reverse the cut direction to remove the scallops. Or when you have steeper sections on the part, like truncated cones or steep drafts, you can also do what is called finishing in levels, which is called horizontal finishing, also known as Z-level finishing, or some systems call it like a waterline finishing. So you can do that as well right from the standard configuration. So this gives you a finishing in levels toolpath, or also known as Z-level finishing.
I get the second one.
Beautiful.
So there's your Z-level finishing. We also have other types of methods where we can do radial and spiral machining. So I could do radial machining, and I can even do just surface selections. I could say I want to pick just these surfaces in here. I can pick those as the surfaces for machining. So you have control for selecting part surfaces as well. You can specify the cut conditions in here, cut parameters. In the cut part surface, I can say I want to go past the surfaces, then generate it. So that'll generate a toolpath just around those areas. So you have radial, you have spiral, horizontal, and parallel finishing as part of the standard configuration. And if you go to a website, or if you have a demo installed, you can actually go into the configurations in the help system in here, and you can learn about what's included in each of the configurations of the product. So what we talked about was the standard, But these are all the methods that you get in the 2.5 axis, and you have these methods in 3 axis: horizontal roughing, parallel finishing, horizontal, radial, and spiral machining.
Okay.
And you get the knowledge bases, so you can take all of these operations that we program, save them into a knowledge base in here. So I'm going to just put it right over here, save it up. Now let's say I want to bring in a different part. I want to work off of a cavity in a core instead of a cavity. I can load the knowledge base and work with it. So once you have the toolpaths programmed, you can look at the estimated time based on the parameters you put in for your feeds and speeds. It'll tell you how long it's going to take to cut it. So this gives you an estimate for machining. And you can also generate a setup information sheet. We call this shop documentation. You can choose a template in here, and then you specify a location where you want this to be saved. This actually creates a HTML report and gives you information about the tools that are being used, the feeds and speeds, the cutting conditions that you put in, and it'll automatically display it in an HTML viewer, like whatever you're using for browsing your internet. And you can save it out.
Cool.
So the shop documentation also comes included from the standard configuration. Now let's look at another example in here. Let's program a core for the same parts. I'm going to go in and look for another file in here. I'm going to grab the core model right here. And what I'm going to show you here is how we can use the knowledge base for programming these parts. So I have the part in here. I'm going to define the stock material.
Oh my God. Oh, man.
And then once I have the stock defined, rather than having to program each and every operation in here, I'm just going to go ahead and say load my knowledge base and go into this folder and pull the knowledge base into it. So now I have my knowledge base. I can just edit it and set the parameters. And I can go into roughing, right-click, and regenerate. So the roughing toolpath is automatically computed based off the part on the stock. I can go to the parallel finishing in here, and I can specify a boundary for containment. So the knowledge base has information about, the parameters that you're using in here. It also gives you information about, the feeds and speeds, all the cut conditions in here. So you can basically, take advantage of the knowledge base to automate your workflow.
Yeah.
So you notice that I didn't have to go back and set any of the parameters because it's being loaded from the knowledge base.
Yeah.
And I can do the same thing in here, radial machining. I can just go ahead and select the surfaces that I'd like to apply for it, these two, generated. And I can do a horizontal finishing in here. And if I want to pick a containment, I could always do that in here. I can say select loop to pick the entire loop around it. So you can take advantage of your selection tools that are available to you in SOLIDWORKS, like select chain, select tangency, select loop for defining the containments. You don't have to go and pick, if you had hundreds of faces or surfaces, you don't have to go and pick each of them.
Yeah, that's a really useful tool. I use that a lot.